Hello students, today we are going to discuss about Gauss law. Okay, and these questions here you can see this is this is asked on Gauss law. So this question was asked in 2020 higher secondary final examination under Assam Higher Secondary Education Council, right? So what is asked here, that a closed spherical surface encloses a charge q at its center, so that electric flux through the enclosed surface is q by epsilon naught. Actually, this is the statement of Gauss law. Actually, Gauss law states that let me write the statement, then you gonna understand the question better. Okay, so Gauss law states that that the total electric flux through any closed surface closed surface is equal to 1 by epsilon naught times the charge enclosed by the closed surface, right? So you need to prove this statement. Actually, in this question you are asked to prove this statement: a closed spherical surface encloses a charge q. That means the closed surface charge enclosed by the closed surface is q, and you need to show that the total flux through this surface is 1 by epsilon naught times of q, right? So that is what you need to show. So let me prove this one actually. So let me take a new slide, okay, in order to prove this. Just wait. So here is the new slide. Okay, so let me write proof of Gauss law. Right, so what we can do here, so first let me take a closed surface here. Let me take the surface. So this is a suppose closed surface. Okay, so here you see at its center, this is the center suppose, and at its center a charge q is there. Okay, so charge q, just let me write q here. According to the question, q charge is enclosed by this closed surface, and which is located at its center. And so let me take its radius be r. Okay, let the radius be r. Okay, let me take that way. So first let me write what I have considered here. So let us consider a spherical surface, closed surface, and of radius r encloses a q charge q at its center o be the center suppose. Okay, so let me write here closed surface. Okay, let me write here closed surface. Just wait, give me a second. Closed surface. Okay, and it encloses a charge q at its center. Okay, so let me take a point here P. This is a point P here. Okay, so let's take a point P, and let me consider an area element, very small area element ds. So very small area element ds. Okay, and here you see, let me write the r properly. This is the radius r. Okay, so let me consider this is positive charge. Okay, then the at this point P, the direction of electric field is normally outward from this. It is radially outward, and this must be normal to the surface ds. Okay, so because radius is always perpendicular at the point of its surface. Okay, so now you see this is going to be the direction of the area vector ds let me take the unit vector along the area vector is suppose n cap. Okay, let me take that way, and here you see, just wait here, and if we consider this center O as origin, and the position vector of P is suppose r given by the r vector radius vector, and then unit vector along this radius is suppose r cap. Let me consider that way. Along the radius is suppose r cap. Okay, just wait, r cap. Then electric field at P. Okay, electric field at P. So what will be the electric field at P? So we know that electric field due to a charge at a distance r, is given by E is equal to 1 by 4 pi epsilon naught q by r square. If the distance from the charge to that point where we need to find the electric field is r, then electric field is given by this expression in vector form. We can write here r cap, which represent the unit vector along this vector. Okay, along this direction. Okay, so hope you understood this. So now, so electric field at P is given by E is equal to 1 by 4 pi epsilon naught q by r square r cap, where r is the unit vector, where r cap is the unit vector along OP. R is the unit vector along OP. So hope you have understood this. So now electric flux, okay, through the area element ds. Okay, electric flux through the small area element ds, as shown here. This is ds, this is the area element, this is the small area element. You can see this is the small area element whose area vector is ds vector, and ds vector is, suppose this is ds vector and its magnitude is ds, and direction is given by the unit vector n cap. So I have considered that n cap is the unit vector along the unit vector of the area vector. We have considered that way, right? So then according to the definition of electric flux, that should be given by we are writing here electric flux through small area element. So let me write d phi, that gonna be equal to E dot ds, area small area ds, area vector ds. So now you see, so electric field, so we can use this one here, right? So if we use this expression of electric field here, what we're gonna have, 4 pi epsilon naught q by r square r cap n dot ds vector, and ds vector, let me write as ds n cap. So where ds vector is equal to ds n cap. N cap is the unit vector of the area vector ds, right? So let me assume that way. Now you see direction of this r vector, direction of this r cap, and the direction of this n cap same. So theta gonna be 0, and cos 0 is 1. So that's why what we're gonna have, r cap dot n cap that's gonna be equal to r cap, magnitude of r cap into magnitude of n cap, that's going to be cos 0 degree, and these are unit vectors, so their magnitude must be 1, and 1 into cos 0 is again 1, right? So that's n cap and r cap, in cap dot r cap, that's going to be that's going to be equal to 1, right? So finally we're going to get this answer, that 4 pi epsilon naught q r square ds. That's what we're going to have, because dot product of r and n cap, that is 1, right? Now this is d phi. D phi is the electric flux through this very small area element, this area element ds. So we need to find the flux through the entire surface, this spherical surface. Okay, so that's what we need. So here you see, so in order to get the flux through this whole surface, we need to integrate the flux through this small area element ds. Okay, so let me copy this expression and let me take a new slide here. Okay, so just let me copy and let me take a new slide. So here, so therefore total flux, right, total flux, or you can say electric flux over the entire surface, over the entire surface. Yes, let me take the area of the let me go back to the previous slide. So let me copy the diagram. So here you see, this is the diagram, right? So let me consider that this surface is S, so total surface area is, so entire surface area is. So in order to obtain this, we have to integrate d phi over this surface, right? So here you see 1 by 4 pi epsilon naught, this part is constant, so q is also constant, r is also constant, q r square. So integration, surface integration of ds, that's what we're going to have. So if you integrate this very small area element ds, then what you're going to have, you're going to get the total area element, total area of the surface, right? Integrating this small area ds over this if you take the surface integration of this small area element ds, then you're going to get the total surface area, right? So then what we're going to have, 4 pi epsilon naught q by r square, and total surface area, let me write it properly, r square, and integration, surface integration of ds, that's going to give you the surface area of this sphere, which is nothing but 4 pi r square, right? So here we're going to write 4 pi r square, phi is equal to 4 pi r square. So here what we can cancel, 4 pi gone, and r square gone, we're going to have q by epsilon naught. So phi is equal to q by epsilon naught, and that is what we needed to prove. So hence it is proved. So hope you have understood this. Thank you for watching. See you in the next video. Okay.